Hello guys, welcome to IGCSE Computer Science, where we'll be going over the first chapter and the first topic, number systems 1.1. Moving on. Um, so there's three types of number systems. There's binary, there's denary, and there's hexadecimal, also known as hex. Denary is the number system we use in our daily life. So it's represented by 0 to 9. So it could be in mathematics, for example, you could be doing addition, 255 plus 10, 265. So it's all represented using denary, and that's the one we're most familiar with. Now, binary is the number system used by computers. So it's either a 0 or a 1. That's because computers have many transistors, which either turn on or off. So when they're on, it's a 1, and when they're off, it's a 0. So that's all they can process information in, either ones or zeros. That's why we use binary in computers and not denary. And finally, there's hexadecimal. So there's applications of hexadecimal later on, so we don't use it in computers, but we use it to represent error codes in computers. But that we'll cover later. So it's represented from 0 to F. Wait, so let me show you guys a hexadecimal table. So as you can see, there's the hex values here, and there's associated binary and denary values. So a 0 in hexadecimal represents a 0 in denary. A 1 in hex represents a 1 in denary, all the way until 9. And then after that, instead of 10, it becomes an A. So an A in hex represents a 10, and a B in hex represents an 11, C in hex 12, D 13, E 14, F 15, so on. So F is the maximum value that is represented in hex. So yeah. So here's how you guys can convert from binary to denary. As you guys can see that the denary values have a binary value associated with it. The denary value 3 has a binary value of 0011. The denary value of 10 has a binary value of 1010. If you guys want to know how to do that, we basically multiply each binary digit by its corresponding positional weights, which is basically powers of 0 from right to left. So these are the correlated values, the positional weights. So this would be 2 to the power of 0, which is 1. This is 2 to the power of 1, which is 2. 2 to the power of 2, which is 4. 8, 16, 32, 64, 128, and so on and so forth. So an easy way to remember this is basically doubling the value of, so we start off with a 1, and then we keep on doubling the value when we move left. So the value after this, so if this number had an extra 1 to the left, the value correlated to that 1 would be 256, 512, 1024, 2048, so on and so forth. So here's how you guys can convert. So if you guys wanted to convert 101, 10101, let's draw that down, shall we? 101, 10101. That's pretty, yep. Now we take the value associated with it, we write down the value associated with it. So 1, 2, 4, 8, 16, 32, 60, 64, and 128. There. Now that we've done that, like the presentation has shown here, we remove the values that are associated with zeros because we don't consider them, we don't count them. And we add the values that are associated with a 1. So as you can see here, I've removed the 64, the 8, and the 2 because it's all associated with a 0. And then I'm going to add the numbers associated with 1s. So here I would be adding 128, 32, 16, 4, and 1, which would result in 181. Okay, I'll just give another example in case this is too confusing. Draw. So if you guys wanted to convert the binary digit 11000011, we again write the values associated with it. So 1, 2, 4, 8, 16, 32, 64, and 128. I know it's kind of spaced too close together, but just, okay, let me just separate that. Okay, there, it's separated now to make it easier for you guys. There. So we then remove the values that are associated with zeros because we're not adding them up. So we're removing the 32, 16, 8, and 4, and we're only adding 128, 64, 2, and 1. So once we add those values, we should get something along the lines of 195. We should get 195. That should be your answer. So I hope you guys understood that. If you guys want to convert denary to binary, so if you guys wanted to do the opposite, let me teach you guys how to do that. So if you guys wanted to convert the denary number 200 into binary, we basically divide this value by 2 all the way until 0, and then we take the remainders. The remainders would be the binary digit. So let me give you guys an example. 200, keep dividing it by 2, okay? So we keep dividing it by 2 until we get 0. So 200 divided by 2 would be 100. And then we put the remainder next to it, so that the remainder would be 0. And 100 divided by 2 would be 50. We take the remainder, which is 0. 50 divided by 2 would be 25. Remainder, 0. 25 divided by 2, sorry, let me just write the 2 properly. 25 divided by 2 would be 12, remainder 1. And 12 divided by 2 would be 6, remainder 0. 6 divided by 2 would be 3, remainder 0. 3 divided by 2 would be 1, remainder 1. And sorry guys, my handwriting's so bad because I'm basically drawing this on a mouse. 1 divided by 2 would be 0, remainder 1. Now we take the value of the we just take the list of remainders and we write it from bottom to top. So the value of 200 here would be 1, 1, 0, 0, 1, 0, 0, 0. There, because we're going from bottom to the top in this direction. So the value of 200, the binary value of 200 would be 1100, 1000. Let me give you guys another example. Suppose we take the number 133, okay? We do the same thing. We divide it by 2 until we get 0, and we take the list of remainders and write it from bottom to top. So 133, divide that by 2 would be, how much would that be? 56? Sorry guys, I'm bad at maths. 66, yep. So we're not allowed to use calculators. So you guys will have to refine your math skills in order to do this fast. 66, so that's 133 divided by 2 would be 66. Remainder 1. 66 divided by 2 would be 33. Remainder 0. 33 divided by 2 would be 16. 16. Remainder 1. 16 divided by 2 would be 8. Remainder 0. 8 divided by 2, 4. Remainder 0. 4 divided by 2 would be 2. Remainder 0. 2 divided by 2 would be 1. 1. Remainder 0. And 1 divided by 2 would be 0. Remainder 1. Right? Now that we've gotten the list of remainders, we just write it from bottom to top. Sorry. We just write it from bottom to top. So here the binary value of 133 would be 1, 0, 0, 0, 0, 1, 0, 1. Simple, easy as that. So that's the binary value of 133. So I hope you guys understood that. So here's how you guys can convert from binary to hexadecimal. Now once you have this table memorized, let me just write this example down for you guys. 1, 1, 0, 0, 0, 0, 1, 1. We just split it into groups of 4, and then we look at the specific hexadecimal value associated with the binary value. So 0011 here would be associated with 3. We write down 3. Now 1100 here would be associated with C. So we would write down C3. So the value of the hex value of the binary digit 11000011 would be C3. Let's look at another example. 1100111110, right? Now we look at the specific values associated with it, split it into groups of 4. Then the value associated with 1110 would be E. Then we write down E. And then 1001 would be 9. So the value of this would be 9E. The hex value of this would be 9E. If we take a bigger example, 100111100001. There. Now this is a significantly bigger example, but the same logic applies here. Split it into groups of 4. Sorry. Oops. Split it into groups of 4. Once we've done that, we look at the specific hex values associated with it. So 0001, that would be 1. 1111 would be F. F would be associated with that. So F. And then 1001 would be 9. So 9. So the value of this would be 9 F1. There. Now if you guys wanted to convert from hexadecimal to denary, it's quite simple actually. Let me draw an example for you. Let me just 4DA. There. Now it's quite similar to converting from binary to denary. Now here in this case we took the position values of 2. So the corresponding positional weights. So this was 2 to the power of 0. This was 2 to the power of 1, 2 to the power of 2, power of 3, power of 4, power of 5, power of 6, power of 7, so on and so forth. Now here, instead of taking to the powers of 2, we use the powers of 16. So here, why is this doubled? Anyways, so here, this would be 16 to the power of 0. Just like how here it was 2 to the power of 0. So this would be 16 to the power of 1, 16 to the power of 2. Now if we simplify this, this would basically be 256, 16, and 1. So these are the associated values. After we find the associated values, we basically multiply them with multiply the hexadecimal values with the associated values and add them up. Now you might be wondering, how can I multiply 16 with D or 1 by A? Well, it's quite straightforward. If we go back to the table, A here is the 10th position in the hex lineup. Is the 10th number in the hex lineup. So this is basically 10. And D here is the 11, 12, 13th number in the lineup. So the D would be 13, A would be A, and then we just multiply 16 by 13 and 1 times 10. So here, this basically would be 256 times 4 plus 16 times 3 plus 1 times, times 10. So this simplified would be, let me just do the maths here. You guys aren't allowed to use calculators, but I'm just doing so to speed up the process. 1, 2, 4, 2. Hopefully that is correct. Yes, that is correct. If we take another example, 64AF. 64AF. Now we do the same thing. This would be 16 to the power of 0, to the power of 1, to the power of 2, to the power of 3. So this would be 1, this would be 16, this would be 256, and 16 to the power of 3. This would be 4096. So we now know it's going to be a large value, but they most likely probably won't give you 4 hex digits to be converted in the exam. So let's do this, shall we? So A is the 10th value and F is the 15th value. So if we do this, this would be 4096 times 6 plus 256 times 4 plus 16 times 10 plus 1 times 15. Okay, let's fast forward. This would be, the value of this would be 25775. So you guys get the gist of it. So what are the practical applications of hexadecimal? Well, it's used in error codes. Now imagine if you're coding and 1 0 in the error code 1 0 0 1 1 1 0 0 1 1 1 1 1. Like if an error code like this pops up, it'd be very hard and very confusing to remember. Now if we converted this binary random error code into a much simpler hexadecimal error code, something like 5BF, this would be much easier to remember than whatever this is. So we use this in error codes to represent error codes. We use it in IPv6 addresses. Now IPv6 addresses will be covered later in other parts of of topic 1 of IGCSE computer science. But yes, it is also used in IPv6 addresses. It's also used in MAC addresses, which we will cover later on. MAC addresses are used to uniquely identify network interface cards, also known as NICs. Again, this is all stuff that's going to come up later. HTML color codes is pretty easy. So each color has a specific color code attached to it. So the color red has this code attached to it. The color green has this code attached to it. And the color blue has this one attached to it. Now this is much easier so we can just type in hexadecimal codes, color codes, to bring up the color that we need. So this is used to represent color codes too. So here's how we do binary addition. Now, as you can see, there's quite a few rules that are given here. So these are the rules for binary addition. 0 plus 0 would mean 0, which is quite simple. 0 plus 1 would also mean 1, which is simple. And 1 plus 0 is 1 also. But 1 plus 1 is 10. It says 0 carry 1, which basically means 10, as we can see here. But let me explain to you why it means 10. So if you convert 1, give me a second, guys. If you convert 1 in binary to denary, it's going to be 1. So 1 in binary is the same as 1 in denary. So if we do 1 plus 1 in denary, let me just write denary over here to not confuse you guys. Denary, it would mean 2. Now, if we convert 2 into binary, which would be, I'm just doing it for you guys, 2 divided by 2 is 1 0 0 1. 1 divided by 2 would be 0, remainder 1. So 2 in binary would be 10. So you guys get it? So 1 plus 1 in binary would mean 10. So if 1 plus 1 in denary is 2, 1 plus 1 in binary would mean 10. So 10 is the same as 10 in binary is the same as 2 in denary. Now, if we move ahead a step, so 1 plus 1 plus 1, that would be 11. So as we can see here, 1 carry 1, which we can see here in this part of the equation. So 1 plus 1 plus 1 is 11, which follows the same logic. So 1 in binary is the same as 1. So 1 in binary is 1 in denary. So 1 plus 1 plus 1 in denary is equal to 3. Now 3 in binary would be 3 divided by 2 is 1, remainder 1. 1 divided by 2 is 0, remainder 1. So 3 in binary would mean 11. So 1 plus 1 plus 1 is 3, which is the same as 1 plus 1 plus 1 is 11. So 1 plus 1 plus 1 in binary would be 11, and so on. And then if you wanted to represent 4 would be 100, I'm pretty sure. Let me just verify that for you guys. 4 plus divided by 2, remainder 0. 2 plus 2 divided by 2, 1, remainder 0. Yep, it would be 1. So a 4 in binary. So 1 plus 1 plus 1 plus 1 in binary would be 100. And it increases incrementally and so on and so forth. So just try to memorize 0 plus 1, which is 1, 1 plus 1, which is 10, and 1 plus 1 plus 1, which is 11. As long as you remember those, I think you'll be fine. You won't need to remember more than that. So let's start off with an example, shall we? If we did 1, 0, 1, 0 plus 0, 1, 0, 1. Oops, that's too simple. 0, 0, 1, 1. Yep. If we wanted to do that, we just look back at the rules here. So first we start with 0 plus 1, which is 1 here. 1 plus 1, which is, as is given in the rules, it's 10. So 1 plus 1 is 10. So it's 0, carry 1. So the 1 gets carried here, and we write 0 here. 1 plus 0 is the same as 1 plus 0 is 1. And then 1 plus 0 is 1 again. So the result of this would be 1, 1, 0, 1. And if we verify this in binary, denary, you guys are free to do so. You guys can convert this to denary and this to denary and add it up and convert that back to binary. It will result in this as the answer. So yeah. Now overflow error. Overflow error is when, let me give you an example again. 1, 1, 1, 1 plus 1, 0, 0, 0. Now let's do this. 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1. And 1 plus 1 is 10, carry 1. Now the 1 doesn't get carried, so we write 10 here. Now this is an overflow error because the amount of bits that addition is being done in cannot fit the answer. So the answer has more bits than the addition it's being done in. So that causes an overflow error. So it's lost. It causes an error. So it can, since the answer is only supposed to be 4 bits and this is holding 5 bits, this one here gets lost. So left shifts and right shifts. Now let's start off with an example. 0, 1, 0, 1, 1, 1, 1, 1. Now if this multiplies to the, if we shift this to the left by 1, so if this, by shifting we mean we shift the entire thing to the left, but then we remove the first digit and we add a 0 at the end. So this would turn into 1, 0, 1, 1, 1, 1, 1, 0. So the rules are basically just keep it in 8 bits, remove the leftmost digit, and add a 0 at the end to the rightmost part of the binary table, binary sum figure. Sorry, you guys get the gist. So if I were to take another example, if I wanted to left shift this to the left by 1, this would be 1, 1, 1, 0, 1, 0, 1, 0. As you can see, I got rid of the 1 and added a 0 at the end. So that's how left shift works. And right shift is basically the same thing, but you shift the entire thing to the right. So let's take this very same example. 0, 1, 1, 1, 0, 1, 0, 1. Sorry, let's take 0, 1, 1, 0, okay? Now if we were to do this thing and shift it to the right by 1, this would be 0, 0, 1, 1, 1, 0, 1, 1. Now, as you can see, we shifted the entire thing to the left, so we removed the 0 here and we added an extra 0 at the left. And we kept this in 8 bits. We kept this 8 bits. So again, we're not changing the number of letters, the number of bits this thing has, we're keeping it 8 bits, but we're removing the bit at the rightmost area and we're adding a 0 at the leftmost thing. So yeah, pretty easy concept to grasp. Let's move on. Oh yeah, and when we left shift, we multiply the entire value by 2. So let me give you an example. 0 1 1 0. Now if we were to convert this into denary, this would be 1 2 4 8. Now we don't count these values, so 4 plus 2 is 6. Now if we were to left shift this by 1, this would turn into 1 1 0 0. So we left shifted this by 1. Now it turns into this. Let's convert this into denary, shall we? And we don't count these, so 8 plus 4 is 12. So we can see that it's multiplied by 12. It got multiplied by 12. And this applies to any example, by the way. So if you shift it to the left by 1, it should be multiplying by 2. Now, let's do that again. 0, 1, 0, 1, 1. 0, 0, 1, 1, 0, 1, 1, 1. Now, if we were to shift this to the left, let's verify that. 1, 4, 8, 16, 32, 64, 128. Cross, cross, cross. 32 plus 16, that would be 48, 52, 54, 55. Now, if we added these values, this would be 55. Now, let's shift that to the left by 1. Let's do this. 1, 2, 4, 8, 16, 32, 64. So you guys don't have to write down the values associated with the zeros. You can just skip that, move on to the next value. So 64 plus 32 would be 96. 96 plus 8 would be 104, 108, 110. And that's 110. So as we can see, the value gets multiplied by 2. It's 2x's. And if we were to do the opposite and right shift this, it would be divided by 2. It would be, yeah, right shift would be divided by 2. Yes, and one more rule. In an 8-bit register, if we were to left shift a value like this, this would be 1 0 0 0 1 1 1 0. If we were to left shift this value, as you can see, this value is lost. So 1 2 3 1 2 4 8 16 32 64 128. So the 128 value is lost. It's gone. It's scratched. So this would cause an overflow error, because yes, that would cause an overflow error. 2's complement. Yes, 2's complement. Let's move on to 2's complement. Now, how would you convert a negative binary digit? Now, how would you convert a negative denary digit into binary? This is where 2's complement comes in. So here, if we were to convert a number like, let's not take 128. Let's take a simpler example, negative 16. Negative 16. Now the first step would be to write the positive version of it. So 16 here. This would turn into 16, and you find the binary version of this as normal. So 16 divided by 2 would be 8 0. 8 remainder 0. 8 divided by 2 would be 4. Remainder 0. 4 divided by 2 would be 2. Remainder 0. 2 divided by 2 would be 1. Remainder 0. 1 divided by 2 would be 0. Remainder 1. So 16 would be 1 0 0 0. 1 0 0 0 0. So that would be the value, and then we just add 2 values in front of it to make it simpler. Just these don't count anyways, but we're converting it into 8 bits for simpler working. And then after that, we convert that so we invert all the bits. So here, we invert all the zeros into ones and ones into zeros. So this would turn into 1 1 1 0 1 1 1 1. And after that, we add 1 to the result. So we add a 1 to this. So after we invert the bits, we just add 1. So we do normal binary addition. Voice crack. So 1 plus 1 would be 10. 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 1 plus 0 would be 1, 1, 1, 1. So this would be the value. So as we can see here, this would be our ones complement value of -16. So I know this might look confusing. You guys might think this is 240, but it depends in the context of the question. So if they ask you the question, if this is given in terms of ones complement, we always assume the leftmost bit to be negative. So this would be -128, and then all the rest would be positive. Now, if you were to convert this back into denary, we would assume the leftmost value as negative. So this would be -128, and then the rest is positive. So here we would be doing -128 plus 64 plus 32 plus 16. So if we do that, the answer would be -16 if we add this up. So yeah, that's a wrap on video 1 of IGCSE Computer Science, and I hope you guys enjoyed this video. Thanks a lot.